Hi everyone, welcome back. So this is still module about beam deflection. Okay, so for the previous videos we discussed about the double integration method. So for this video we're going to discuss problems about area moment method. But before we go with area moment method, let me first show you the relationship. Okay, so you have here a simply supported beam from point A to point C. So this is point A, point B, point C. So we need to determine the deformation at point B. So what we're going to do is to create a relationship from point B to point A. So we draw here a tangential line from point A with respect to your deformation. Okay, so here we have the deformation at B and we have our tangential line. So this is the tangential deviation between B relative to A. Okay, so we can now solve deflection at B by a trigonometric function of tangent. So tangent is equivalent to opposite over adjacent. So tangent theta is equivalent to the deformation at B plus the tangential deviation from point B relative to A. Okay, but we have two unknowns. We have three unknowns. We have the deformation at B. We have the tangential uh, deviation from B relative to A, and we have the unknown theta A. The tangential deviation can be solved via area evaluated from point B to point A times the lever arm. But theta A is unknown. So what we're going to do is to have or to use the similar triangle. So we have here the tangential deviation from point C relative to point A, and we can create a right triangle. So tangent theta is equivalent to TC over A divided by the length. Okay, but please be reminded that our deformation is very small. Okay, therefore the angle here is also very small. So if the angle is very small, we can say that tangent theta is equivalent to theta itself. Okay, so theta is equivalent to the tangential deviation from C relative to A divided by L. TC over A can be computed via area of the moment diagram evaluated from point A to point C times the lever arm relative to C. Okay, so substituting it there, we can now solve for our theta. So theta A is equivalent to the deformation at B plus the tangential deviation of B relative to A divided by X. Okay, so we have theta, we have X, we have unknown deformation B and tangential B over A. So to solve tangential B over A, it is simply the area of the moment over E diagram evaluated from A to B times the lever arm with respect to B, right? Because we are evaluating here, so our X bar would be relative to B. Okay, then we already know our TBA, so substitute it there. We can now solve for the deformation at B. So cross multiply, transpose to the other side, then this is now our working equation for the deformation at B. Okay, so we have here example number 3 from your module. A 600 pound-feet uniformly distributed load is applied to the left half of the cantilever beam. So from point A to point B, kalahati lang siya. Okay, so determine the magnitude of force P. We need to determine the value of P. Okay, shown so that the displacement at A is equivalent to 0. So dapat daw theta A is equivalent to 0. Okay, so before we do that, let's try to analyze how would our curve look like. So theta A is 0 and we have here a fixed support at the right end. So if I am to draw my elastic curve, it would look like this. Okay? Since this is a fixed end, the deformation at C is equivalent to 0 and theta C is also equivalent to 0. But according to our condition, theta A should be 0. Okay? So since we are evaluating from P, the tangential deviation of A relative to C is equivalent to 0. So the tangential deviation of A relative to C is equivalent to 0. This is our tangent at C because the tangent here is horizontal. So straight lang siya. So the tangential deviation of A relative to C is 0. Hindi tayo makakagawa ng ganitong line because according to the condition, it should be 0. Okay? So, ganyan ang naging itsura niyan. Hindi tayo nakagawa ng straight line to create the relativity. Okay? So, with that, we can now solve for the value of P. So, tangential deviation of A relative to C is simply equivalent to the area of M over EI diagram evaluated from A to C times X bar with respect to A. So we will be having our lever arm with respect to A. Okay? But we cannot yet proceed in drawing our moment. If you see a problem like this, like what we have discussed previously, pag putol yung load natin, what we need to do is to create a continuous load, to add a continuous load. Then to cancel that out, I'll be having another continuous load at the bottom, but with opposite direction. Okay, so I already draw it firsthand. So we have here P, and we have here 600 pound per feet. So 600 pound per feet. According to the procedure, kailangan yung mga reaction, we need to convert that into an applied load. So here we do not need to do that because we will be using the left support for our what do we call that, conversion of cantilever beam. But in the first place, it is a cantilever beam, so we don't need to solve for any reaction then convert it to any applied load. Okay, so like what I've said, I added a continuous load here of 600 pound per feet, and I will cancel that out by introducing a uniformly distributed load at the bottom but with opposite direction. Okay, so to solve for TC, TC over A, which is equivalent to 0, I will just be simply drawing the moment diagram by parts. What do we mean by parts? The moment diagram of each of the load separately. Kasi it is easier to determine the maximum moment and at the same time the lever arm. Okay, so we have here a point load. If our load diagram started with point load, the shear would be a 0 degree and the moment is first degree. Okay, so we have P times a distance of P. Therefore, the value here is 8P, and that is a triangular load. Okay. Next, we have here 600 pound per foot. On the load diagram, it is a uniformly distributed load that is 0 degree. Shear diagram, first degree. Then, for the moment diagram, it is a second degree curve. So, it will be a second degree curve, and take note, it is pointing downward. So, it is negative. So, it would look like this. Okay, so for the value, it is simply 600 times the span of 8 feet, so that would be 600 times 8, so that is now converted into a point load, times the lever arm, 4,800 times the lever arm of 4 feet. So we now have 19,200, but that is negative. Negative 19,200. Okay, we're not yet done because we still have the 600 pound feet, and that is pointing upwards. Okay, so we need to draw that on the positive direction since it is positive, pointing upwards. Okay, so 600 times a span of 4 feet times a lever arm of 2 feet, so that is 4,800. That is positive. And that is a second degree curve. So it would look like this. Now take note, we are evaluating with respect to A, TC, the tangential deviation of A relative to C. Okay, so we need to determine the lever arm of each moment diagram to with respect to A, x bar with respect to A. So the centroid here, we know that for a rectangle, the centroid is 1/3 from the base. So since that is 1/3 from the base, we know that this is 1/3. So this is 2/3. 2/3 of 8. Next, we have here 3/4. So we have here 3/4 from the top, or 1/4 from the base. So that would be our lever arm. So 3/4 of 8. Next, for the last diagram, we know that this is simply 3/4 from the top plus 4, because this is 4, then this is 3/4 of 4. So we have 3/4 of 4, then 4. Okay, then we are now ready to make our equation. So with that, we can now determine the value of P. So the first is, we have 8P. So 0 is equivalent to 8P height times the base of 8 times 0.5, because that is a triangular in shape, times the lever arm, and the lever arm is 2/3 of 8, positive yan, then this one is negative because it is on the negative side. So minus, we have 19,200. That is the height times the base of 8. So that is AH over 3 for a parabola or spandrel. AH over 3 times, what is the lever arm? The lever arm is 3/4 times 8. Then we have here the last diagram, that is plus. So plus 4,800 times a base of 4 divided by 3, area of a spandrel, times the lever arm of, this will cancel out, so that is 7. Therefore, P is equivalent to 1,537.5 pounds. And that is the final answer. I have here problem number 4. A simply supported beam in the figure shows, which is supporting a concentrated load of 300 Newton. So EI now is equivalent to 20.48 times 10 raised to 3, and that is in Newton meter squared. Okay, so determine the slope angle of the elastic curve at A. So we need to determine theta A, and we also need to determine the displacement at point D. Okay, so that point D is 1 meter. So that is 1 meter from the left support. So this is point D. Okay, so what we need to do first is to solve for the reaction, but of course the reaction here is already given. The next thing we need to do is to convert one of these two support into a fixed support. Then the other support would be converted as an applied load. Okay, so I'll be choosing point A, B, C. So this is A, B, C. I'll be choosing point C because I will be determining the slope at A. So that would be a lot easier. Okay, so in doing so, this is point C, then the rest would be an applied force. So we have here an applied load of 100, and here we have an applied load of 300. So this is now my free body diagram. This is point D here, and that is 1 meter from the left support. Okay, so the first thing to do is to determine the deflection at A. So that would be, take note that this is a simply supported beam. So the deflection of a simply supported beam would look like this. Okay, it would look like this. So if that would be the case, I will be having here a tangential line from point A to point C, and the tangential deviation of C relative to A is this. Okay, then from there I can have angle theta A. Okay, so since tangent theta is almost equal to theta, we can write theta A is equivalent to tangential deviation of C relative to A divided by a length of 3. Okay, so length of 3 meters. So how are we going to solve for theta A? First, we need to solve for TCA. So TCA is equivalent to the area of the moment over EI diagram evaluated from A to C times the X bar with respect to C. Okay? Kasi nandito yung ating support. Okay? Nandito yung ating TCA. Nandiyan yung TCA natin. Okay? So, let's draw the moment diagram. So, for the moment diagram, it is by parts. Moment diagram by parts. So, that would be P. Not P. It is 100. So, 100 times a lever arm of 3. So, this is a point load. For the shear, it is 0 degree. For the moment, it is first degree. So, 100 times 3, that is equivalent to 300. And that is a triangular load. So, we have here 300. Next, we have a point load of 300, but it is pointing downwards. So, it is negative. Okay? So, 300 times 1, again, that is also 300, but it is negative. So, for the lever arm, we are going to have our lever arm with respect to C. Okay? So, because TCA is here. So, the lever arm is 1/3 from the base. And that 1/3 is of 3. So cancel out. It is simply 1. Next, we have here the lever arm. 1/3 of 1 is also equivalent to 1/3. So we are now ready to determine our TCA. So TCA is equivalent to factor out natin si EI because we already have a value for EI. What is EI? EI is 20.48 times 10 raised to 3. So 1. So factoring out, we have the area here. What is the area here? 300 times a span of 3. So 300 times a span of 3 times 0.5 because it is a triangular load times the lever arm of 1 minus, because it is on the negative side, minus we have 300 times a span of 1 times 0.5 for because it is a triangular load times the lever arm of 1/3. Okay, TCA therefore is equivalent to 0.01953, and that is in meters. That is the TCA. So since I already have my TCA here, I can substitute there to solve for theta A. Okay, so theta A therefore is equivalent to divided by 3. So this is 6.51 times 10 raised to negative 3. And this is in rad. Okay? To convert that into degree, we have pi is equivalent to 180. So times pi over, baliktad. This is now equivalent to 0.373 degrees. That is now our theta A. And it is positive. Okay? So therefore, it is a counterclockwise. Isn't it clockwise? So if it is clockwise positive, it is counter then negative for A. Next, we need to determine the deformation at B. So here, we need to determine the deflection or the deformation at D. So the displacement at D is simply the area of the area of D for the moment diagram. So if I am to project that to our diagram, it will only be this. So the area times the lever arm. Ito lang yung lever arm natin because we are evaluating D. Okay? At D. So that would be the tangential deviation of D with respect to A is equivalent to the area of M over EI diagram evaluated from A to D times X bar with respect to D. Okay? So with respect to D. So if we are to exaggerate this or to highlight that, it would look like this. Okay? So this is displacement D. Then this is tangential deviation of B, because this at point D rather. Point D relative to A. And we have here theta A. Okay? So theta A is equivalent to we have the the displacement D plus the tangential deviation of D relative to A divided by a distance of 1 meter. So here we have A, we have the X, which is 1 meter. We can solve for TDA. So for TDA is equivalent to EI. What is our EI? EI is 20. So 20.48 times 10 raised to 3. Okay? And next we have the area. Ano yung area nito? So we have a base of 1 meter times a height of, what is the height there? So we can use similar triangles. So 300 so 300 is to 3, y is to 1 meter. So actually by observation kaya nang malaman yan. Y is by inspection, y is equivalent to 100. So we have here 100. So times 0.5, because it is a triangular load, times the lever arm. What is the lever arm? The lever arm here would be 1/3 from the base, and that is 1/3 of 1. So yan yung lever arm natin. Ang base natin is yung D. Okay, kung saan tayo nag-evaluate. So we have 1/3. Therefore, TDA is equivalent to 8.138 times 10 raised to negative 4. Okay, and this is in meters. So substituting, what is theta A? Theta A is 0. No. Gamitin natin si rad, because here it is radian. Okay, we just converted this one to degree. So radian, we have 6.51 times 10 raised to negative 3 is equivalent to the displacement D plus what is TDA, 8.138 times 10 raised to negative 4 meters divided by 1. Okay? Or you can also use the radian here, given that you convert 8.138 times 10 raised to negative 4 into no. This is in meters pala. This is in the angle. No. It is meters. So we convert, or we can not convert. We use the radian mode, or the radian unit. So for this, so shift solve, or if you want to equate it as displacement D, we can do so. So displacement D is equivalent to 6.51 times 10 raised to negative 3, that is radian, times 1 meter. Transpose this to the other side of the equation, minus 8.138 times 10 raised to negative 4. So the displacement at B is equivalent to 5 5.696 times 10 raised to negative 3 meters. So we convert that into mm. Okay? Times 1,000. So that is the displacement is equivalent to 5.7 mm. And that is our final answer. So we have here problem number 5, a simply supported beam with an overhang. It is loaded by a 150-pound force and a 30-pound force. So according to your module, we need to determine the EI displacement at the end, or that is point D. So this is A, B, C, and D. So how are we going to do that? It is better if we are going to imagine how would my curve look like. Okay. In doing so, we will be asking the aid of this very elastic ruler. Okay. So take note, you have a support at A and a support at B. So how would I do that? So imagine this ruler is your beam and you have a load at 150. So it would deflect this way. And you also have a load of 30 at D. So it would deflect this way. So the deformation of the ruler would most likely be the image of your elastic curve. Okay? So you have here A, support, and a support at C. So your curve would look like this. Okay. So if I am to draw my elastic curve, my point of tangency for the slope, it would look like this. Okay. So if I am to blow up this portion, we are having this. And this is the curve, the elastic curve. So this is the deflection or displacement D, and this now is the tangential deviation of D relative to C. Tangential deviation of D relative to point C. And from there, we can have theta C because this is point C. So theta C is equivalent to the tangential deviation of D relative to C plus displacement D divided by 4 feet. Okay, 4 feet. We can solve for tangential deviation of D relative to C by getting the moment diagram, but theta C is unknown. Okay? So, from supplementary angles, theta C here is also equivalent to the theta C here. Okay? So, having a relationship there, we can say, or we can solve theta C by theta C is equivalent to the tangential deviation of A relative to C over the length of 10 feet, or that is simply TOA, tangent opposite over hypotenuse. But tangent theta C is also equivalent to theta C. So tangential deviation of A relative to C divided by the length of 10 feet. So we can solve TAC and TAD using our moment diagram by parts. So redrawing that, we have this. Okay, so according to our procedure, it is best if we substitute one of our support and yung pinaka-convenient. And I think the most convenient one would be C. Okay, so what I'm going to do is to place here a fixed support at C. So this is now a fixed support. Then draw the moment diagram by parts. So you have here a 100. You have here a point load or an applied load of 100. We converted, no, it's not 100. We converted our support as an applied load. So this is not 100, rather 78 pounds. Then we have here a 150 pounds. And we have here a 30 pounds. Okay, so this is now my free body diagram. But if you want to include here the shear C, we can do so. So this is 102. So from there, we can now easily draw our moment diagram by parts. Alright, so 78 times a span of, this is 4 feet, 6 feet, and this is 4 feet as well. So 78 times a lever arm of 10, so that is 780, and it is a triangular load. So that is 780. Next, we have here 150, and it is pointing downwards. Therefore, it is a negative loading. Okay, so 150 times a lever arm of 6. So that is 900. Next, we have 300 times a lever arm of 30 rather, 120, and it is negative. Negative 120. So TAC, the tangential deviation of A relative to C, is equivalent to the area of M over EI evaluated from, we have here A to C, times the lever arm with respect to saan? Is it at point C or is it at point A? Take note, theta, TAC is what we are evaluating. So that is with respect to A. Okay? So the lever arm that we are going to use would be with respect to A. So this would be the lever arm. So we have this is 10 feet. So that is 2/3 of 10. And this is this is 6. What is 2/3 of 6? 2/3 of 6 plus 4 feet. That would be the lever arm. So TAC is now equivalent to the area 780 height times a span of 10 feet times 0.5, because that is a triangular load, times the lever arm of what is our lever arm? 2/3 of 10. Is it positive or negative? It is positive because it is on the upper side of our reference. Next, we have this area here. So for the area here, that is minus, because it is below our baseline of 0. So minus 900, yun yung height natin, times a span of 6 feet. So times 6, times 0.5 because it is a triangular load times the lever arm. So what is 2/3 of 6? That is 4. Yes, plus 4, that is 8. A lever arm of 8. And that's it. TAC is equivalent to 4,400. Take note that we still have EI over here. EIN. Okay? We were not given the value of EI. Therefore, EITAC is equivalent to 440 pound-feet cube. So we now have our TAC. Then, meron tayong distance na 10. We can now solve for theta C. So, substitute natin. It's equivalent to 4,400 divided by 10 feet. So, this is equivalent to 440 pound-feet squared. Because that is cubed, then that is feet. So, magka-cancel out. Okay, so we already have our theta C. So, since we already have our theta C, we can now solve for tangential deviation. Kasi we have here theta C is equivalent to the tangential deviation of D relative to C plus displacement D. So, let's solve for the tangential deviation of D relative to C. So, we can solve for displacement. Okay, so that is simply equivalent to the area of M over EI times, evaluated from C to D. This time, ano yung X bar natin? Yung X bar natin would be relative to D. Because take note, ang hinahanap natin ngayon dito is this, we are evaluating at this side. Okay? So, that is with respect to D. Okay? So, ang hahanapin nating lever arm would be, if this is 120, if this is 4 feet, the lever arm here is 2/3 of 4. Okay? So, TDC is equivalent to, we have the height of 120 times the base of 4 times the lever arm of 2/3 of 4 times 0.5 because that is a triangular load. Okay? And take note, it is on the negative side, so that is negative. So, TDC is equal to negative 640. And that is EI, tangential deviation of D relative to C. Okay? So, can we now solve for our displacement D? Yes. So, substituting the values, theta C is equivalent to the tangential deviation of D relative to C plus displacement D divided by 4 feet. Okay, so what is our theta C? Theta C is 440 is equivalent to what is TDC? Negative 640 plus displacement D divided by 4. Okay, so cross multiply, we have 440 times 4 plus 640 is equivalent to the uh, displacement D times EI. Take note, we have EI there. Okay, EI here, EI here. Then we have EI. Kasi we were not given the EI. So it is in terms of EI. Wait lang, wait. This should be positive. It should be positive 640 because the negative sign here is just an indication that it is pointing downwards. Okay, because the tangent the displacement D is below the tangential line. Okay, but this is positive 640 pound feet cube. Okay, so that is positive. We have here negative. So we have here 440 times 4 minus 640 is equivalent to displacement D. Displacement D is equivalent to 440 times 4 minus 640, and that is 1120 pound feet cube over EI. So that is the final value. It is positive here because it is indicating that displacement D is above our reference line, which is this. So kaya positive. Yung kanina na solve natin is negative because it is indicating that it is below. Anyways, the sign is just an indication of whether the displacement is above or deflection is above or it is below our reference line. Okay?